Volcanoes look like isolated mountains until the moment they open. One day the ground trembles, gas vents, ash climbs into the sky, and a local landscape is rewritten. Now imagine that moment happening everywhere at once. By every volcano, we mean the roughly 1,350 potentially active volcanoes identified by volcanologists, those that have erupted at least once in the last 10,000 years. About 500 of them have erupted during recorded human history. These are overwhelmingly the volcanoes on land and in shallow coastal waters. They do not include the continuous volcanic belts along the mid-ocean ridges, where new seafloor is created every day as tectonic plates slowly pull apart. Those submarine systems already release magma steadily. The thought experiment focuses on the discrete, named volcanoes that can produce sudden, concentrated eruptions. Even restricted this way, the scenario is still extreme. These 1,350 volcanoes do not share a single connected magma system. Each is fed by its own local reservoir of molten rock. An eruption begins when gas-rich magma rises, pressure builds, and the rock above gives way. For every one of them to reach that critical point on the same day would require an improbable coincidence of independent processes. Yet examining the consequences still reveals how volcanic gases, ash, and heat interact with the atmosphere and with human systems. Not every volcano would produce a massive explosion. Some, especially basaltic ones, such as those in Hawaii or Iceland, tend toward quieter lava flows that advance at walking pace. Others, particularly those with more viscous, gas-rich magma, can generate powerful, explosive eruptions that send ash columns tens of kilometers high and unleash pyroclastic flows, dense mixtures of hot gas and rock fragments that race downslope at high speed. Underwater or coastal volcanoes could displace seawater and trigger local tsunamis within hours. Ash would darken skies near each erupting vent, collapse roofs under its weight, clog engines and filters, and make outdoor breathing hazardous. Air travel across large regions would halt. Power and water systems near major eruptions would fail. The immediate human cost would be severe in densely populated volcanic zones, though exact numbers cannot be known with any precision. The global effects, however, would not come primarily from the lava or the pyroclastic flows. They would come from what reaches the atmosphere when magma rises, dissolved gases escape. 2. Matter most for climate: sulfur dioxide and carbon dioxide. Sulfur dioxide is the more powerful short-term agent. If it reaches the stratosphere, it reacts with water vapor to form tiny droplets of sulfuric acid, sulfate aerosols. These particles are highly effective at reflecting incoming sunlight back into space, reducing the energy that reaches Earth's surface. The result is cooling. Ash behaves differently. Larger ash particles fall out of the atmosphere within days or weeks. Finer ash can linger longer and travel farther, but it does not stay aloft for years the way sulfate aerosols can. This distinction is important. Many people imagine a volcanic winter as a world permanently choked by ash. In reality, the longer-lasting cooling comes mainly from the sulfur chemistry, high above the weather systems that would otherwise wash particles out. We already have clear observations from individual large eruptions. In 1815, Mount Tambora ejected more than 100 cubic kilometers of material. The following year became known as the year without a summer. Global average temperatures fell by roughly half a degree Celsius, with stronger regional effects. Crops failed across Europe and North America. Snow fell in parts of New England in June. The 1991 eruption of Mount Pinatubo produced a similar global cooling of about 0.5 degrees that lasted a couple of years. If hundreds of volcanoes erupted together, the combined injection of sulfur dioxide would be far larger than any single historical event. The exact temperature drop cannot be calculated with certainty because it depends on how much sulfur each volcano releases, how high the plumes rise, and how the aerosols spread. What is clear from atmospheric physics is that the cooling would be substantial and global monsoon patterns would weaken or shift. Growing seasons would shorten. Frosts could strike in places that rarely experience them. Reduced sunlight and ash-contaminated soils would lower agricultural yields across multiple continents at once. The entire planet would not become pitch black. Near major eruptions, the sky would darken dramatically for days or weeks. Farther away, a gray haze and vivid sunsets would be more likely than total darkness. Still, the reduction in sunlight reaching the surface would be enough to disrupt photosynthesis and the climate systems that depend on it. Volcanic carbon dioxide would also enter the atmosphere. Over long timescales, volcanoes help regulate the carbon cycle. In the short term, however, the cooling from sulfate aerosols would dominate. Even a simultaneous eruption of all 1,350 potentially active volcanoes would release far less carbon dioxide than human industrial activity currently produces each year. Any warming effect from the extra CO2 would be secondary and would arrive after the aerosols had already begun to settle. Volcanoes far from population centers would still matter. A remote eruption that injects sulfur high into the stratosphere can spread aerosols around the globe within weeks, affecting climate everywhere. The location of the vent influences local destruction, but the atmospheric chemistry does not respect national borders. After the initial phase, the planet would enter a multi-year recovery. Sulfate aerosols gradually fall out of the stratosphere over 1 to 3 years as particles grow, coagulate, and descend. Sunlight would return. Temperatures would climb back toward previous averages, ash layers would begin to weather, releasing nutrients that can eventually enrich soils. One reason volcanic regions are often fertile once the immediate hazards pass. Life has survived larger volcanic events in Earth's past. The Toba eruption roughly 74,000 years ago was a far bigger single event than anything in historical time. Some researchers have suggested it contributed to a bottleneck in human population, though that interpretation remains debated and is not settled science. What is clear is that humanity and countless other species endured. Even the largest known volcanic episodes did not sterilize the planet. In the simultaneous scenario, the greatest risk to modern civilization would not be the extinction of our species. It would be the simultaneous failure of the complex systems that support billions of people, global food trade, energy grids, transportation networks, and public health infrastructure. Regions distant from any volcano would still face shortened growing seasons, economic disruption, and migration pressures. How long the major atmospheric effects lasted would depend on the total sulfur released in atmospheric circulation, but the most intense cooling would likely ease within a few years as the aerosols cleared. The thought experiment also highlights something fundamental about Earth's internal engine. Volcanoes are surface expressions of the planet's ongoing effort to shed internal heat. Plate tectonics and mantle convection drive the movement of magma over geological time. These same processes have helped recycle carbon, build continents, and create conditions that make complex life possible. The forces that can darken the sky for years also renew the surface and influence the long-term climate. A simultaneous eruption of every potentially active volcano is not a realistic near-term risk. The magma chambers are independent. The chance that all of them reach critical pressure on the same day is effectively zero. What the scenario makes visible is the sensitivity of the climate system to sudden sulfur injections, the difference between short-lived ash and longer-lasting aerosols, and the degree to which modern civilization depends on stable growing seasons and relatively clear skies. If every one of those 1,350 volcanoes erupted at once, the immediate result would be widespread. Local destruction followed by a volcanic winter strong enough to challenge agriculture and infrastructure worldwide. Temperatures would fall, sunlight would diminish, food systems would strain, yet the Earth itself would continue. The aerosols would eventually settle, the climate would recover. And the same volcanic processes that caused the crisis would, over longer timescales, continue to shape the planet's surface and atmosphere. The extreme scenario simply makes visible what is always true. The ground beneath us is not static, and the atmosphere above us responds quickly to what rises from below.